Go ahead and go over this one. So let's go through first. Are these two elements, this pair of elements, going to form an ionic compound? Calcium and fluorine? Yes, okay, I see something else. Good. How do we know that?
Is calcium the metal? Fluorine is
Good. You need a metal and a non-metal. Good. How about sodium and sulfur? Yes, good. How about fluorine and sodium? Yes, good. And rubidium and iodine? Good. Okay, so these are all going to form ionic compounds. Then we need to write our formula. So what would the formula be for this compound that forms between calcium and fluorine? Good. CaF2. Can you remind us how to get there?
Oh, okay, to balance out the charges.
Good. Okay. Can you walk us through it?
Oh, so calcium has a charge of 2+.
Good.
And then fluorine has a charge of just one negative charge.
One negative. Good. So to get
the net ionic charge to be 0, you have to get 2 fluorines to balance out the
good.
2 positive charge.
Perfect. Good. So we need 2 of these, 2 minus charges to 1 2 plus charge. Good. And what would we call this?
Calcium fluoride.
So
wait, no, it's ionic.
It's ionic.
So it'll just be calcium fluoride.
Good. Calcium fluoride. Good. Okay, and then be really careful on spelling. Spelling matters. If you get the spelling wrong, then it's going to be wrong. Okay. All right. How about this one? Sodium and sulfur. What would our formula be?
NaS2. I guess I'll just answer all of these.
Okay. NaS. So be careful on this one. Sulfur has a 2 minus. Sodium has a plus.
Oh,
so we need
mind,
2. This one's tricky. So sorry, 2 Na. Okay. Good. Okay, and what would we call this?
Would you put a prefix on sodium?
Nope, no prefixes because it's ionic.
Okay, so just sodium sulfide.
So just sodium sulfide, good. And no capitals. That's a U. Okay. How about this one? What would the formula be for a compound with sodium and fluorine? Good. Why did you put Na first, even though it came second?
Because that's the metal.
Yeah, good. Metal has to go first. Good.
Or
the cation. Good. Yeah, cation or metal goes first. Good. Okay, how about this one? Good. Rb. Rubidium. Oops. Rb and I. Good. Rubidium is +1. Iodine is -1. So you just need 1 of each. Good. So what would this be called? Oh, we skipped that one. What would this one be called? The bottom one. Good. Rubidium iodide. Good. And then I think we skipped this one. What would this be called? Good. Sodium fluoride. Good. Okay. We did this question. I started going back, and this was one of the most missed questions on chapter 3 test. So that's what I'm kind of looking at to help us review. How do you guys feel about this one now? Do you guys feel okay? Do you have questions on that? Okay. All right. So let's go to our calendar. So we're going to switch up chapter 13. I thought we were going to take 3 days, but I think we can fit it into 2 days. And then we'll have 3 final review days. So instead of just having 2 final review days, we're going to squish everything, and it's not really a squish, we're going to compress chapter 13 into 2 days. We'll do a review day, and then we'll have chapter 13 test. Okay, and then we'll have 3 final review days in class. Okay. All right, so some things to not forget about. Don't forget that you need to be working on chapter 13, Alex. After we get through all of chapter 13, you can have 100% high progress. We'll have covered all of the topics. So be working on that as we're reviewing for the final and working on chapter 13. If you haven't turned in lab 34, make sure you turn in lab 34. The last day, we have about a week. The last day to turn that in is next Tuesday. Okay. So make sure you get that in. Don't forget about the signature assignment. And then if you are done with all the labs, make sure you get if you borrow the lab book from me, make sure you get that back to me. Okay. All right, questions about our schedule or any questions about our assignments? Okay. All right, so we're gonna continue with chapter 13. Okay, start chapter 13. Let me pull up our slides. So this is more organic chemistry, but now we're going to talk about what to do if there's a double bond or a triple bond. Okay. So the first thing is what happens if there's a double bond? If you have a double bond, this is called an alkene. So we change the ending instead of ane, we use ene, and that's called an alkene. Something also that's interesting that sometimes can help us is that alkenes have a general formula of carbon. However many carbons there are, there's twice as many hydrogens if you just have one double bond. So this alkene is, we just have two carbons. This is ethyl. We have two carbons, that's our two carbon group is ethyl, but instead of ethane, this is Fe. So we just changed that ending to ene. And I think we've talked about this a little bit before, but if you have a double bond, then your bonds, if you look at this carbon, we have 3 groups around this carbon. So the angles between the bonds is 120 degrees. So if you have a double bond, that's called an alkene. Okay, the next one is an alkyne. If we have a triple bond in our molecule, then that's in our alkyne family. All right, so we just have YNE instead of ANE instead of ENE. Okay, so this is a triple bond carbon, and like we've talked about before, if we have a bond where if we have an atom and it has 2 things bonded to it, then the bond angles are 180 degrees. I remember I have a handout for chapter 15. Okay, the next thing that we're going to talk about is naming. So the naming rules are on this paper. You can also write them down if you want. The naming rules are pretty similar to what we've been talking about. Okay, first we're going to talk about this. All right, so if we have an alkene or an alkyne, so if we have a molecule with a double bond or a triple bond, that's called an unsaturated hydrocarbon. So we've been just talking about saturated hydrocarbons. Our molecules have been saturated with hydrogen. If there's a double bond or a triple bond, then the molecule isn't saturated with hydrogens. That's called unsaturated. Have you guys heard of that before? Unsaturated food. Good, and fat and food. So fats can be saturated fat or unsaturated fat. That's what they're talking about. If it's saturated, then the whole molecule has all the hydrogens it could possibly have. If it's unsaturated, then it has some kind of, usually double bond. So that's kind of interesting. Our vocabulary is Some of us have heard about this before. Okay. Something to watch out for is when you are drawing a condensed structure, you have to draw the multiple bond. So you can't just show that there's less hydrogens. You need to show, if there's a double bond here, you need to show that in the condensed structure. Okay. And in Alex, to do that, you just click on one carbon and click on the other carbon, and it'll draw the double bond in there. Okay, questions so far? Okay. All right, so this is our naming. So we've seen this before. We use the prefix to tell us what substituents we have on the longest chain and where they are. The parent tells us where the longest chain is, and the suffix tells us the group. So we've been using ane as the suffix because we just have boring carbons, no double bonds, no triple bonds. Now, if we have a double bond in our molecule, we're going to use ene as the suffix. If we have a triple bond, we're going to use yne as a suffix. Okay, so now we need to watch out for that. If there's no double or triple bonds, we are still going to use ane for ane. Okay, so this is, I think most of these rules are on there, but you can write them down again if you want. So we're going to, if we have a double or a triple bond, we're going to number the carbon chain so that the double or triple bond has the smallest number. We don't care about anything else. We want to prioritize the double or triple bond. So here's an example down here. We have one butene, excuse me. So we have 1, 2, 3, 4 carbons. We're going to number this way because it includes the double bond and it makes the double bond the smallest. Does that make sense? Okay, and then we could add the methyl later. So this one over here, we have 1 carbon, then 2 carbons. So this double bond is between the second and third carbon. We number from the first carbon. So the first carbon that the double bond sees. Okay, so it could be, it's between the second and third, we call it, that's at the 2 position. Does that make sense? Okay, so if we count this molecule, we've got 1, 2, 3, 4, 5, 6. So that's hex, that's our prefix, and then ine is our suffix because we have a triple bond. And the triple bond is at the 2 carbon. Okay. Questions on that? Pretty straightforward. Okay. All right, and then here is the rest of our rules that are on your sheet. So we're gonna number the main chain just like we've been doing. We're going to find the double or triple bond just like we just talked about. Make sure the triple or double bond is at the lowest number that we can. And then we need to specify where that double or triple bond is. If it's at the 2 position, we need to say that double bond is at 2. And we'll do some examples. In Alex, if the double or triple bond is at 1, it's optional if you want to put it's at the 1 position or not. It's optional. I would stick with and be consistent. I would just always tell yourself where that double or triple bond is, even if it's at 1. But just know if you leave that off, if it's at the first position, it doesn't seem to matter. And then you're going to name your parent, and then you also need to, just like we've been doing, if there's methyl groups, if there's ethyl groups, you need to write where those are and their numbers. Okay, so this is just like an add-on of chapter 12. Okay, so keep all the rules from chapter 12. We're just adding a little bit for double electric bonds. Okay, questions on that? Let's do an example. So all of these molecules are hexane, but they have a double bond, so we're going to call them hexene. And then I have to tell you where the double bond is. So here, the double bond is between the 1 and 2 carbon, so I'm going to call this 1 hexene. Okay. Over here, we have a carbon, so we've got 1, 2, 3. This double bond is between the 2 and the 3 position, so this is going to be 2 hexene. So then over here we've got 1, 2, 3, or if we count it this way, 1, 2, 3. So it doesn't matter. This is 3 hexene. Okay. All right, questions on that? Okay. All right, go ahead and try these molecules. See if you can name them. Yeah. That's more common. But it's then they prioritize. There's like that. Multiples to get prioritized. Okay, are you ready? What would you call this molecule? Okay, good. So this would be called, let me turn on our pen. This would be 4-octene. Good. Okay, how about this one? Good. Sorry, I didn't count it already. So 1 and E. Good. Okay, questions on that? Is that pretty straightforward? Okay. All right. So now, if we have something in the middle and we have a group off to the side, do you want to try this one or do you want me to do this one? I have a few more. I'll do it. You're fixed. Okay, so we're trying to make this first. We want the double bond to be first, but if we can make our side groups first, or if we can lower them, we will also do that. Because if I count it this way, 1, 2, 3, 4, then I have a double bond at 2, and I also have that methyl group at 2. If I count it the other way, 1, 2, 3, 4, then I have the double bond at 2, but I have the methyl group at 3. So it's probably better to go this way to reduce our side chain and keep our double bond at the lowest group. Yes.
So will you still use the rule where it was like you can add the positions and whatever position is lowest?
For the side chains, but you don't really care about that much, not as much as the.
Like if it's on the same.
Oh yes, yeah. If it's on the same, if it's symmetrical, yes. But you want to prioritize the double bond or the triple bond. That should be lowest no matter what. Okay, good. Okay, so what this one would be called? We have 4 carbons in our longest chain. What's that called? Good. We have bu, and then we have a double bond, so we have to say that has a double bond. I'm going to say the double bond is at 2, And I have a methyl group at 2. So I have 2 dash methyl, and then between a letter and a number I put a dash. So that would be our name, 2-methyl 2-butane. Okay. Hey, do you guys want to try this one? Or do you want to walk through one more?
I'm okay.
You want to try it?
We should.
We
try
should do it? Okay, let's do it. So we care most about our double bond, okay? So look at this double bond, or look at our parent chain. What would our longest carbon chain, how many carbons would that have? So this one's a chlorine. So
I didn't see that.
1, 2, 3. And so if we start here, then this is going to be first. So 1, 2, 3. Okay. And our methyl group would be at 2, and we have a chloro group at 1. So what is our parent carbon chain called if we have 3? Propene. Good. Propene. Okay, and we need to tell where the double bond is. This one is kind of optional. I think it's a good idea to just stick with always tell where the double bond is, even if it's at 1. Okay, so we've got 1 propene. And then how do we decide what to tell first? Do we say the chlorine or the methyl group? Good, why? Because, good, alphabetical. So 1 dash chloro dash 2 dash methyl dash 1 protein. Okay, questions on that? All right, here's one for you to try. So, yeah, if it has a All right, are you ready? You ready? Okay, so what would you call this molecule? Do you want to share with us?
Sure. 4 dash methyl dash 1 dash pentene.
Okay, do you agree with that? Okay, good. All right. Oh, I must not have. Okay, so on Alex, you will also have to draw these. I must not have fixed my slides. Sorry about that. Okay, so now we need to talk for a minute about rigid parts of molecules. So I have some models up here. So if I was going to draw this molecule out, I would have a carbon, and then this represents a double bond to another carbon, okay? And then I have a hydroxide group over here, so OH, okay? So this is what it's supposed to be representing is that a single bond, around a single bond I can rotate. This one doesn't work super well, but we can imagine that rotates pretty well, okay? But if I carbon-carbon double bond, that's really hard to rotate. It'll twist a little bit, but it's not going to rotate all the way around that, okay? So this helps us know, there's a question in Alex that's gonna ask you to decide, it'll have different distances, and you have to decide if those distances can change or not. So the distance between this hydrogen and this hydrogen, because there's a single bond here, that hydrogen-hydrogen distance can change, okay? But if I look up here, because there's a double bond between these adjacent carbons, these two hydrogens are not going to change distances, okay? So anytime there's a double bond, that's gonna lock in your molecule, okay? So there's parts of the molecule that can rotate around a single bond, and there's parts that cannot rotate. They cannot rotate around a double bond, okay? Also, keep in mind that this carbon is attached to this hydrogen. That bond length is not going to change. So this is not going to change. The hydrogen to hydrogen bond on the same carbon is not going to change, okay? Does that make sense? Okay, so I'm gonna pass these around and you can kind of look at that. So that Alex question, it really helps me to think in 3D and think about what does the molecule actually look like in 3D. Okay. All right, I also have this simulation we're gonna look at for a minute. And this is another way to imagine this. So up here I have a rotate button. This is ethane, and I can spin it. So if I was looking at the distance between this hydrogen to this hydrogen, and I rotated this single bond, the distances between all the hydrogens are going to change. Let's see if I can. There, oh, there it was. There we go. Can you see that? So the distances between the hydrogens on this carbon and this carbon, so this hydrogen to this hydrogen, those are going to change because that single bond can rotate. But the distance between this carbon and this hydrogen are stuck. And the distance between this hydrogen on the same carbon is also stuck. Okay? All right. I think that's hard for me unless I imagine it in 3D. Okay, I also like this one. This is called triphenyl. We have two phenyl groups attached together. This group in the middle is a single bond. And if we rotate that single bond, we can see that the hydrogens are going to get closer or further away depending on how that single bond is rotated. Okay? But the distances between these hydrogens are not going to change because these carbons are locked in a ring. Does that make sense? Okay. So just kind of imagine the molecules that they give you in a 3D space. Oh, and there's one more. There's a double bond. That's that thing. This is the one. And we can also try, just like in our model, we can try to rotate around the double bond, but it just kind of flexes. We can't really. So this, the distance between these is not going to move much, and between these two is not going to move much because they're locked by that double bond. Okay, questions on that? All right. Yeah, of course.
I guys don't know me, but I teach this up on Weaver Takes campus, and this is one of the harder topics in this chapter. So you guys are gonna get a great advantage, like be able to like hold it and try to move it and see that, because this topic in Alex is a little bit of a bear. So just kind of keep your eyes out for it early, maybe start working on that one early so you make sure you get through that one, because this one's a little bit tough. Yeah, we just finished up our test on this one specifically, so that's why it's like fresh in my mind.
Okay, thank you. Okay, thanks. All right. That's right page. Lost my mouse. I have my mouse up there. Let me see if I can click on it. There we go. Okay, we did both of those. Okay, the last thing that we're going to talk about today is this vocabulary word called an isomer. So an isomer is a molecule. It has the same chemical formula, but it's a different molecule. So we have two up here. They both have 3 carbons. They both have 7 hydrogens. They both have a bromine. But the bromine on this one is connected in the middle, and the bromine on this one is connected on the end. So they're different molecules, but they have the same formula. So that's called an isomer. Okay. So you're going to have to decide if a molecule is an isomer or if it's not an isomer. So this is what I would ask myself if I'm trying to decide if it's an isomer or not. So do they have the same chemical formula? They have to have the same chemical formula. If they don't have the same chemical formula, then they can't be isomers. Okay? And then the second question is, are they different molecules? Because sometimes you can have the same molecule, but you can draw it in a different way, and then it's the same molecule. So it has to be a different molecule, and it has to have the same chemical structure. Okay? So let's look at this example. So go ahead and see if these are isomers, and also see, are these isomers? Do they have the same chemical formula, but they're different? All right, are you guys ready to talk about this one? You ready? Okay. So the best way I know how to do this is to just do it the long, tedious way and write the whole formula out for both molecules and check. Okay, that's I think the best way. So let's look at this molecule. We have carbon with 3 hydrogens. We have carbon with 2 hydrogens. And carbon with 3 hydrogens. So what did you guys get? What is your formula?
C5H12.
Okay, you guys agree with that? Okay, and then let's check over here. So first we can also look, is this the same molecule? No, this has a different structure. So let's check. What is your formula for this one? Maybe?
Yes.
Yes? Okay. So we can also, I think the long, tedious way is sometimes the most reliable. So we can also just write it out. And we've got 1, 2, 3, 4, 5 carbons, 6, 9, 10, 11, 12, 13, 12, wait, 9, 10, 11, 12, 13. Am I doing, what did I do? Oh, this one should only have 1. Okay. Okay, so we've got 12. All right, so are these different molecules? Do they have the same formula? Are these isomers? So yes, these are isomers. Good. Okay, how about this one? You're saying no. Tell us why you think that.
It's the same molecule.
It's the same molecule. Good, but rotated. if we pick this molecule up and we flip it around and lay it down, or if we like folded this here, this would line up on top of each other exactly. So this one is not an isomer because it's the same molecule. Okay. Does that make sense? All right. Okay, so that's our last topic for today. We have, I think you'll be able to do all but 2 of the topics. You can try to do them without us. I have the slides posted, but we'll go over the last, I think, maybe I can't remember if there's 2 or 3 left. But try to get some of the Alex done. If you haven't turned in the lab, make sure you do that. You could also work on the signature assignment. I think we're getting down to that. Or you could also work on the final, study for the final. Okay. All right.
Oh, Dr.
Yeah. Oh, you just put them on the desk for a minute.